Okay, my name is Foong. Just a bit about myself. I'm an academic staff at NYP, Nanyang Poly. I've been here for about 2.5 years, and I teach iOS programming for specialist diploma and full-time course students. And on top of that, I actually am still heavily involved with projects and with external customers doing full-stack development and what have you. Before that, I was working as a chief software architect in a local startup for about 8 years, designing software products for corporate as well as government customers. And today I'm really happy to be here to share about Apple's machine learning frameworks with a bit of a focus and tilt towards natural language processing. But I'm not here today to say which machine learning algorithms are the most accurate. No, we leave that to the experts. I'm just here to share with you how we can use some of these frameworks in our apps. All right, so we're going to talk a little bit about conversational UI. So what is a conversational UI? So think Siri, Alexa, Google, basically a free-form dialogue with the machine where inputs to your machine can either be spoken or typed. So I'm going to jump straight into this question: can we build our own Siri? Well, yes, to some extent by using Apple's frameworks. But why do we want to build our own? Already available today in the market, we have a good number of cloud solutions for us to cherry pick. And the reason why you want to roll your own, maybe it's you want to save costs, you want to safeguard your customers' data, you want to implement custom logic that cloud solutions cannot provide, you want to explore various machine learning kits so that we can build other things, kind of like myself, or to do this in the name of learning and research, or simply just for fun. All right. Now, for me, using speech to instruct the computer instead of programming, it's kind of like the ultimate holy grail. And wouldn't it be good for us to say to our computers, hey, show me all my expenditures from January last year until today. And it understands exactly what to do and really does it for you. And wouldn't it be great, right, if we could feed our computers functional specifications, functional specifications, and it spits out code for me. That would be great, right? But of course, if we do that, right, if we ever reach that point in time, all of us will be out of a job. But nonetheless, it doesn't stop us from trying. And now programming the computer with voice using natural language today is still some time away, fortunately for us. But we do see a gradual but rising trend to implement conversational user interfaces, aka chatbots, right, in various apps and services. Now, a standard conversational UI starts with the user supplying a sentence to the machine. Then the machine processes the sentence, understands it, and performs whatever that is requested by the user, and usually replies back to the user. But that ghost in that little shell of our phones has to do a lot of complicated stuff that we humans find it so easy to achieve. Now let's take a look at some of the things that our machine has to do. Number one is the ability to convert recorded speech waveform into text, to perform some natural language processing to parse and prepare your text, and then use some state-of-the-art engines to identify the intent. The intent is simply what the user wants to achieve. And in machine language lingo, we call it classification. Oops. Beg your pardon. Now, then the last step is actually to perform intent recognition. So intent recognition is a process where you extract entities from your text that forms the parameters of your intent. For example, if the user says, I want to book a flight to New York, then the intent is really to book a flight, but the destination, which is the parameter of your intent, is right, New York. So once we have the intent and the entities, this is when we move on to actually code the logic required to fulfill the user's intent. But since that is pretty much logic that we can code, we won't cover that here. And there's usually also that final component that I mentioned just now, where the machine will synthesize a response back to the user. Again, I won't be covering that here. All right? So let's talk about speech recognition. Now, since WWDC 2016, Apple released the SpeechFramework, allowing all apps to now incorporate speech recognition without us having to subscribe to third-party services. Now, the speech framework is pretty cool. It supports up to 62 locales based on what I checked yesterday. Obviously, it supports English. Sadly, it doesn't support Singlish. Okay? It's okay with Singaporean accented English, but not the local colorful flavor that you either love or you find it really odd. Okay? Now, to have speech recognition in your app, what needs to be done? Pretty much what you have to do for your cameras, your GPS, and so on and so forth, you get permissions, right? You actually update your info plist first, right? For your descriptions. Then you get your permissions. Then you initialize your audio engine, right? Then after that, you initialize your recognizer, okay? And this is where we actually code the result handler that will be called every time the speech is recognized. Now, there is a property that's called should report partial results that tells the recognition task that it's okay for us to receive the partial recognition results as the user is speaking and as the server continuously improves its best matches. Now, in the result handler, we can inspect the return results and print it to the console or display in our labels or what have you. Now, once we've prepared everything, the audio session and the recognition request, we hook these two up together, and then we start our engines, right? This is when your microphone turns on and recording starts. Yeah. Okay. So, what's good about Speech Framework and what's not so good? The good thing is that it's really easy to include it in your code, and it's always great for short utterances. Apple, based on the last I checked yesterday, they actually provide 1,000 requests per device per hour. That's a lot. Okay, that's really generous. But it has a maximum of 1 minute duration. So any request that you make to turn on a microphone, send a waveform to the server, that has to be a max of 1 minute. You can go longer than that, right? But you can send multiple requests subsequently. The last thing that I usually face is sometimes Siri doesn't like me, right? So it can't hear me very well. Let's talk about natural language processing with this NS Linguistic Tagger. Now, what NS Linguistic Tagger is it offers us a means to parse any sentence, to identify parts of speech, or to extract word stems, okay, from all words in a sentence. Now, this is the code that initializes and calls your linguistic tagger. This part initializes the tagger. This part calls on the tagger to analyze and return results to the handler. Now, what's important here is actually the tag scheme. There is a scheme there, parameters that you pass into the enumerate tags function. The tag scheme is the one that actually tells the tagger what kind of result that you want to return from it. Let's take a look at some examples. So in this case, if your tag scheme is a language, then if you have this input, what you get is every word will be tagged with English as what the linguistic tagger recognizes. Now, if the tag scheme is lemma, then what we're asking the tagger to do is to return to us word stems. So this is the input, and this is the output. Okay. Now, word stems may be helpful to your use case. In our app, we actually use word stems to reduce overfitting when trying to perform recognition. So what else can you extract? As I mentioned, you can actually extract parts of speech, for example, nouns, verbs, prepositions, and what have you. It can also extract entities, but only restricted to locations, person names, organization names. Now, we're coming to the more fun part of things, CoreML. So CoreML was introduced early this year in WWDC 17, and it now provides us with a way to incorporate machine learning and code learning into our apps. For CoreML to work, you must bundle a pre-trained model file into your application. And that also means that your CoreML model needs to be installed together with your app into the user's device. Well, the advantage of doing this is that you don't really require a full-blown back-end server to handle machine learning tasks. And the fact that CoreML can offload some of the repetitive arithmetic to the GPU's cores, it can run fairly efficiently on a mobile device. But there's an inherent problem. Because your model is bundled together with your app, the CoreML framework can only use that pre-trained model to perform recognition or prediction. It's unable to perform incremental training specific to that device and that user, and to improve that model as we go along. So, which is why I said CoreML, the L part, the learning part, doesn't quite live up to its promise. Not just yet. Hopefully in the future it will be. Well, let's take a look at how we can use CoreML to help us with our intent recognition. Intent recognition, as I mentioned, is a process of discovering what the user intends to do based on the command given to the machine. So one of the effective ways to doing that, right, is actually a very traditional model called the bag of words model. Now what this does is that it simply takes all the words in the sentence, cut them out individually, put them in the bag and mix it up. Right? Kind of like Scrabble and banana grams if you play them, just that now it's words, not letters. So then we give the bag to the machine. So the machine will open the bag, take a look at what's inside, but he has no idea what the original sentence looks like. So based only on the words it sees, it tries to classify the intent. So this is an example. If you saw these two sentences, the words are all jumbled up. Right? You can actually kind of identify what the user wants, right? It's not too difficult. Right? So bag of words work great for short sentences that are short, and you don't have too much ways of actually rearranging them such that they still make sense. Now, bag of words don't really work well on these kind of sentences where the original meaning could have been very well the dog beat the cat or the cat beat the dog. Okay? But nonetheless, we can see how we can use bag of words. And basically, given this sentence, if you pass through a processor, you can actually represent your bag of words through a very large vector or a long histogram, if you will. The x-axis of your histogram will be the full set of words from your dictionary, whereas the y-axis will be the number of words that's found in that sentence for that particular word. Okay? Because the number of elements is huge, the resulting factor is usually very high dimension. Okay, but in our app case, because we're doing this experimentation, we kind of made the words small in size, and we only capture those that we have seen in the training data. Right, those we don't see, we actually put it into a big basket of an unknown word. Okay. Now, given this bag of words, we're going to pass it into a fully interconnected neural network, and we're going to expect it to give an output similar to this. So, input from the top, the output is the intent, okay? And the scores are the probabilistic scores of all your possible intents. And obviously, the one with the highest probability is the recognized intent. Now, a typical single hidden neural network layer looks like this, but we just represented it with the 3 layered boxes for simplicity. This is an example of some of the training utterances that we have. Basically, it doesn't really look like that, but we kind of simplified it for the talk so it's easier for us to understand. So let's take a look at some of the words here. We have create and we have remove, and then we have, that's on the utterance side, and the right side is intent. We have table add and table remove. So we convert that into a dictionary, and then we pick up the index of the word in those dictionaries and reform this CSV file. And if in your input CSV on the left side, you have create, which has an index of 2, and the word remove, which has an index of 8. In the output, which has a separate dictionary, the table add has an index of 0, and your table remove has an index of 1. Then in Python, we load up the CSVs with NumPy, and then we do further processing to turn the input CSV into bag of words vectors. Now the output actually turns, we turn it into what we call a one-hot vector. One-hot vector is basically, the number of elements in this one-hot vector is basically as many as your intents, all right? All of the values are 0 except for 1, which is the one you want to recognize. Finally, our input and output training vectors needs to be fed into Keras. So Keras is actually a machine learning framework in Python, okay? But we need to use Keras with a TensorFlow backend, otherwise we will not be able to export the models into CoreML to be used in our app later on. So let's break this down a little. We have our layers, and then we have our training, and then we have This last part, which is very important, is our CoreML tools. Now, these CoreML tools are tools provided by Apple to be able to export your Keras models into CoreML files. It's okay. I think there was interference. All right, so once you do your training, Keras will spit out this. And in our model, we actually have 99.5% accuracy for seen data, about 98% for unseen data. Okay, so once you have generated your ML model files, you can import them into your project workspace and make sure the target is set to your app. And after that, Xcode will auto-generate the Swift wrapper classes for your model. So to actually do the prediction within Swift using CoreML, this is basically how it looks like. Okay, so let's break this down. This is your input. Okay, this is basically your vector that corresponds to the total number of words in your dictionary. Okay, I beg your pardon. The size of this vector corresponds to the total number of words in your dictionary. Okay, then this part is where the neural network would do its magic. And then finally, you have your output. Your output vector will correspond to the total number of intents. Okay, and the one with the highest probability is the one with your recognized intent. So pretty cool. So what's good about bag of words and what's not? As I mentioned, is great for short utterances that have words that don't really relate to each other. It's not so good for long sentences or short ones that can be rearranged in many ways and still make sense. But finally, because the sequence is lost, we are unable to extract parameters or entities from the bag of words. So we move on to another solution. This brings us to the last part in your grand scheme of things, which is your entity recognition. Now, we can still use CoreML to do entity recognition, but this time using a different neural network called RNN/LSTM. Anybody know what that means? No? Recurrent neural network, right? Yes, very good. So, and this is where, again, things get a little bit interesting. It works a little bit differently from the multi-layer perceptron that we saw just now. But let's talk about some of these abbreviations. NER is name entity recognition. It's kind of like lingo for extracting parameters. We have a recurrent neural network. What this means is that your neural network feeds back to itself after recognition. Now, this allows RNNs to recognize sequences because they have some form of inherent memory due to that feedback mechanism. Now, it's complicated mathematics. I don't even understand, right? Then we have LSTM. LSTM is long short-term memory. It's a special case of RNN with even more complicated maths. Okay, but I use it because it's like, the more state-of-the-art stuff. Now, for our LSTM to work, we're going to have to tag each word in our sentences. And for those that we want to recognize as parameters to extract, we tag them with VB. Those that we want to ignore, we just tag them with O. Now, in some cases, some entities may take up to 2 words. So we have another form of abbreviation, another form of tag to recognize them, to tag them. Then I think to myself, can we also classify the sequence and recognize the intent at the same time? I mean, no harm trying. So what we did was we added an ending marker. We tagged the entire sequence with our intention and send it to the LSTM for training. So let's take a look at how we actually operate now, okay, the LSTM. So the first word show gets sent into the LSTM, and the LSTM is expected to spit out O. Obviously, during training, we hold the input and the output steady, but we adjust the weights inside the LSTM. Right? What's important here is the thing on the left, there's this state. This state is spit out by our LSTM, and then it will be used as an input to our next step, because this will form the memory of our LSTM. So the previous state 1 now becomes input into the LSTM together with your second word. And this previous state input, as I mentioned, is the one that keeps the memory, but keep in mind, because we're going to revisit this important idea later. And then it keeps going, so state 2, word 3 goes into LSTM, and so on and so forth, right? So now that we are here, let's open up the black box a little bit. And looks like complicated stuff, right? Okay, let's focus on a few things. The input to our LSTM is going to be one single value, index of the word in the dictionary, and then the word embedding does some math magic to this index to produce a vector. There's some state outputs on the left, and you have outputs coming out from the bottom. Okay, so these outputs are either the tag for the word or your intent. So these are some sample utterances used for training and corresponding tags. And for example, you have, I want to track my unknown marker and the ending marker. And corresponding on the right side, you have the each word's tag. So the words on the left and the tags on the right are converted to their dictionary indexes. They are also padded, okay, because Keras requires a fixed length to be sent into your training for all utterances. So this is the code for training. Let's break this down again. Now these are the layers. There's an embedding layer, there's a LSTM, and there's a dense output layer. And then we have the training, and finally, this part here outputs your model to your CoreML file. So assuming that we have imported the model into our Xcode project, workspace, and all the Swift files auto-generated, this is how you're going to call the model. This looks a little bit different because we are not going to be sending in the whole sentence into our model at once. We're going to do them word by word. That's why we have that big loop outside. This portion here is the input for the individual word. As you can see, the top part actually says, for the very first word, I'm just going to input the word index. But for the subsequent words, I'm going to input the word index followed by the states of the previous output. Then this is where magic happens. And finally, we collect our results. Again, the one with the greatest probability is the one with the recognized tag and intent. Okay, so LSTM is great at long sequences, able to tag words. You can therefore extract data, but it needs a lot of training data. And so if you're using LSTM, I wish you all the best fun in tagging. Right, we're going to do a little demo later on, but before we talk about it, this demo is actually a part of an app that we probably be using as a base to allow users to manage simple personal databases using just voice as well as typewritten text. So you're going to see me issuing commands for table and record operations using a more English natural language manner. So let's take a look at how this app puts everything that we have discussed together. We allow text input through our software keyboard. We allow speech recognition input. Both of them will actually feed the sentence into NS Linguistic Tagger for word stemming. We then use a combination of LSTM and bag of words together side by side. We use LSTM first, but if this guy doesn't give us the results we want, we turn to our bag of words as a fallback. And then we output our intent as well as the entities. Okay, so let me switch over and do a little demo. Okay, I've got a couple of test cases. Why can't I move my... Okay. So let's say I don't see anything. Gosh. Where's my mouse? There you go. So I've got a couple of use cases, assuming that this app is new and there's no data that's collecting. So I want to instruct the application to create a new table called my expenditure. All right, so when I hit recognize, this sentence get passed into my models, and actually recognize the intent as table add with a probability of 0.99%. Okay, the extracted entities here are expenditure. Okay, let's try a couple of other cases. It has a number field called spend amount. All right, so it recognizes correctly, this is the expected output, that this is a field name for that particular table, and two entities are recognized. One is the number, this represents the type of our field. The second one is actually the name of our field. Okay, and let's say I've already created my tables. I want to add a new entry into expenditure. Right, so this is insertion. Recognized probability is 0.98. Okay, and the table knows to insert into its expenditure, and then I'm going to key in some fields, right? So the description is party after party at, where is it? Clarke Quay? Huh? Brewworks. Brewworks is at Clarke Quay, right? Brewworks. Right. Okay, so it knows that it's going to insert one field with this name. The field name is description, and the actual text is after party at Brewworks. Then insert one more. The spend amount is, say I'm feeling generous tonight. How many people are there in the audience? I won't be there, unfortunately. Okay, it's 5,000, right? So spend amount is the field name, and the actual value is 5,000. So we can do this based on using data that we have seen. I just want to show if I can move this into the front. Right, so this is what our LSTM has been trying to recognize, right? So the very last record, it actually recognizes it as a record data intent with a very high probability of 0.87. For the rest, right, it's almost insignificant. Okay, so actually, with this LSTM that we have trained, it's actually able to do pretty well, right? But of course, the model needs a lot of refinement, a lot of much more data than we have now. Let's see. I could try to run my QuickTime. Let me try and set up this so that I can show this here. Oops. Right. So, oops. How do I move this? You see that? Okay. So, in this app running on my phone, because I'm using SpeechFramework, so it has to run on a mobile device, I can hit the start recording button here to record my voice. Okay, so let me try it. I don't know whether it works well with the echo, but I'll just try. Create a table called expenditure. Right, so speech recognition is able to pull out the text, transcribe my text, and then pass it into my LSTM for recognition. Okay, so let me head back to my slides. Okay, I'm almost done. Okay, so let me just run out. CoreML is currently not able to learn and improve on the fly. However, you can actually download models from the internet and use them. So you can actually have them trained on the server somewhere, and users can download them. But there are some big gotchas, because if your input vectors and your output vectors change in dimensions, that means you may have more words in your dictionary or more intents. Remember, Swift auto-generates your classes for those ML models. If those change, then your code may potentially bomb. And if you also change your layers and all your neurons and everything, all those may stop working as well. So you just have to be careful about that. CoreML not only provides these layers, there are actually a lot of things that CoreML provides. It provides what's the neural networks that's very popular these days, convolutional neural nets. It also has many classifiers, for example, random forests, your conditional random fields, and SVMs, and so on and so forth. Apple also has a vision framework that allows your app to track objects, detect faces, and so on. And if you're not feeling up to creating your own models and training them, you can always make use of pre-trained models. Apple has provided some pre-trained models that recognizes some 1,000 different categories of objects in an image. Or you can obtain them from various research institutions and convert them to CoreML models on your own. Okay, so that's pretty much for my topic. The code that I've used for the demo today is on GitHub if you're interested. If you have any questions, you can always contact me at this email address. So thank you. Thank you, guys.
Thank you, Kim, for showing us how to use machine learning to have a better experience. And any questions from the floor? Okay, I guess no, but you can still look for him during breaks.
Yep.
Yeah, okay, he'll still be around.
Yep.
Okay, still can look for him during breaks. Yeah, and another round of applause for Kim Phone.